Well, hello, everyone. Welcome to our editorial webinar series. And the event today is Engineering Focus on Motion Control, Part 1. My name is Mike Weitzman. I'm the founder of the Mobile Robot Guide and senior editor of robotics at the Robot Report. I'll be your host today. This is our first of two webinars this year exploring some of the latest technology for motion control for robotics. Every month, I look forward to bringing you some of the leading voices in the robotics industry, and I've got two industry leaders on the program this morning who I'll introduce in a moment. But before I get started, I have a few housekeeping items to cover. First of all of the sessions in our webinar series are available on demand. You can rewatch them shortly after they end at therobotreport.com. And you can now go back to any of the prior sessions that you might have missed and rewatch them at your leisure. If you're rewatching a session, just use the same login information that you used today to watch a session on demand. You can also personalize your experience by adjusting the webinar's window size, moving the widgets around on the control panel. Now, at the end of the presentation, we'll have a question and answer period. But as we're talking today, if you have any questions, you can certainly use the designated Q&A widget to submit your questions at any time throughout the session. Finally, if you experience any technical difficulties, first try refreshing your browser window first. This typically solves 99% of the technical issues, or you can always access our webinar producer by clicking on the Help widget. Now, I want to remind you, we've got you covered with all of the latest news and information and education about robotics at our portfolio of sites that include the Robot Report and Automated Warehouse. And before we get started with the session today, I'd like to thank our sponsors that make today's content possible, starting with Novanta. Novanta delivers precision motion technologies for medical and advanced industrial OEMs. You can find more at novanta.com. Bokers, precision manufacturer of custom metal stampings, washers, and spacers. Learn more at bokers.com. Meanwhile, global manufacturer of over 10,000 standard industrial power supply solutions. Learn more at meanwell.com. And finally, Electrocraft, a global provider of electric motors and drives, including application-engineered fractional horsepower motor and motion products. Learn more at electrocraft.com. And with that, I'd like to welcome our speakers for today's webinars. I'll introduce them one after the other. First, I'd like to introduce Andrew Singletary. He's the CEO and co-founder of 3Laws Robotics. Andrew, welcome to the show. Why don't you tell us a bit about yourself and 3Laws?
Hey, thanks for having me. Like you said, my name's Andrew. I started 3Laws about 3 years ago after finishing my PhD from Caltech in robotics and control theory. And what 3Laws does is really provide safe, real-time collision avoidance and other kind of constraint satisfaction for any type of robotic system. We work with mobile robots, manipulators, mobile manipulators, all the way up to humanoids. And you can see a video on the screen now of our software on all of these different robots. Essentially, the fleet manager is doing nothing to kind of deconflict these robots from running into each other. It's the 3Laws software that's running on the robots, preventing, unnecessary interactions, I'd say, between these different robotic systems.
And then our next guest is Robert Brooks. He's CEO and founder of Force N. Robert, welcome to the show. Tell us a little bit about yourself and Force N.
All right. Well, thanks for having me, Mike. I guess similar story to Andrew, except I'm a lot older. I started Force N about 11 years ago, also after finishing my PhD, but out of the University of Toronto, working on next generation sensing and actuation around surgical robots. We started Force N actually building haptic control and safety force systems for surgical robots, and the really purely on teleoperation, no real intelligence or autonomy, and then expanding to logistics, and now doing work in humanoids and physical AI and in some other critical industries. At Forcen, we make force torque sensors and edge intelligence. So we make the fingers, the joints, the wrists, and the ankles for your surgical, humanoid, and logistics robots. And our, I guess, unique advantage in building those sensors is that we make our own transducers so they don't drift over time, over temperature. They're incredibly lightweight, so you can deploy them on something like a humanoid or even a drone. They have dedicated overload, so they can survive impacts and falls and, well, even just like swinging a hammer. And we provide all of the calibration accuracy rated out of the bus and rated right out of the box that can connect to standard bus. So this is really designed to be a bolt it in, plug it in, and get into controls. So yeah, that's us.
Great. Well, what I wanted to do on the conversation today was really take a look at motion control. You know, the other things that exist outside of the PID loop. We've had many webinars in the past with motor producers talking about some of those hardware aspects, and so as you can see, we've got a variety of ways we can go with this conversation today. And I really wanted to look at some of the other things like force control and like the elements that Robert just introduced us to. I mean, Andrew just introduced us to about some of the upper level supervisory control elements for motion as well. So Andrew, let's start with you. And the first question that I want to talk about relative to the things that you do in the part of the motion stack that 3Laws sits in is talk about the integration of AI into the motion control architecture and how that's evolved over the last decade. So let's start there. You give us some idea of where you sit in the world of motion and robotics and how AI is influenced where we exist today when it comes to robotics and motion control.
Sure. I like to think of, different layers of planning and control when I think of robotic systems. You have a, really high level kind of decision-making layer. Then you have what I'd call kind of the motion planning layer, like what are the trajectories of the system going to look like? And then lastly, you have the actual control layer. And I think that AI is really starting to touch, all of these different layers. And 3Laws operates at all of these different layers as well. But I think what we're really starting to see is AI and advanced techniques being used at all three layers of that stack. I think it started more at the top at the decision-making level, but now we're going kind of all the way down to these whole body learned controls, where even the low-level control loop is an AI learned policy. I think the architectures that have proven to be the most successful over time are hybrid architectures, where you do have the kind of stability of traditional kind of deterministic control systems, PID loops, math-like control barrier functions that we use at 3Laws, while also leveraging the capability of AI for, uncertainty, for all these sorts of, hard to model parameters, things like friction, things like contact forces. So I really see it being kind of baked in and integrated, and less of a kind of, AI is taking over controls in motion planning.
Yeah, and thanks for starting there. And I think that's really where the basis of where I wanted to begin some of our conversation today. When we talk about AI being involved there in the evolution of deterministic control architectures, coded PID loops, that type of thing, tuning of axes, right? A classic problem for any controls engineer when you set up a system for the first time to get all those control variables determined and set up and optimized. And now with AI in that, it sort of changes how this whole process evolves. But let's talk about some of let's start with sort of the safety concerns when AI isn't a part of any of these different levels of the motion control architecture. What are some of the concerns there?
Yeah, I mean, I think the core concern is that these are inherently, non-deterministic systems, and their failure modes are really hard to predict. When you look at a traditional control system, you can analyze the stability margins. You can understand what the worst case behavior looks like. When an AI system falls out of distribution, you don't really know what that's going to look like until it happens. And so I think the question becomes like, how can you use and how can you constrain AI in such a way where you can take advantage of all the performance benefits, but it doesn't kind of compromise the safety of the system. And that's really where I think these hybrid architectures come in, where you have these, physics-based, model-based control methods acting as almost like a force field around what the AI might do, so that when different things happen, you don't have this really uncertain, unstable failure mode.
Good. Well, we're not done with that conversation. We'll come back to that a little bit later on in the program. So, but thanks for sort of setting the baseline for that. I want to go to Robert for a moment in a similar question, but with the integration of force feedback, Robert, in what you do at ForceIn. So, talk about how the sensory perception today is integrated into these AI-based control architectures.
Yeah, there's been a real evolution from force control as a force limiter. What we used to call cobots. It would stop the robot from applying force. And then before that was surgical robots on pure teleoperation. We might magnify it, but it was always a direct communication. Now with AI coming in, force isn't just a safety guard, it's also a rich input. So we've worked a lot on visual language models, and now we're starting to work on force language models. So classifiers at the edge. So when you bump into something, not only do you know that you bumped into it, but was it a steel post? Was it a tree? Was it made of wood? Was it potentially a person? Was it squishy? And you can get a lot of context out of bumping into things, just like a human would. If you go around and you hit something, you're pretty sure you hit a steel post, and that has a very potentially different response than if you hit a tree or you knocked a person over. So you can get a lot of context there, and that also allows you to classify things. So a good example is, you can reach into a backpack. You can tell the robot, hey, go and get me a pen out of my backpack. And it can reach in there and it can feel around and it can figure out what's the material, what's the shape, is it hollow? It can do a lot of that classification, classify the material at the edge, classify the behavior, the structure of it, and it can feed that up so that the higher level decision making can say, oh, it's metal, it's hollow, it's about, I have these contact points I've made, so I have a little point cloud. That's a pen. Yeah, let's go and grab that. And that high level planning can feed that up. So I think it's important to think of force similar to the way that you would vision as potentially an incredibly rich input, the same way that humans use our hands.
I've had a chance to play with the intuitive surgical device, to experiment with actually interacting with it. I was amazed at how quickly the learning curve was for me. In terms of being able to sense the feedback of the device operating and to learn from that and to very quickly find myself, embedded into the situation that I was doing with just a few minutes of interaction. And I have to appreciate what that means for surgeons to quickly learn to use a system like that. But if we talk about how AI is being deployed today to train control architectures, is it feasible now to actually model things like force sensing accurately in digital twins so that you can invoke training architectures to actually have the AI learn to use that information as it would in the real world?
So some good news from a solid mechanics perspective. We're fantastic at it. You can get robots to dance, to do parkour, to maneuver around, to really to interact with any sort of solid, dry area. And that is a lot of the factory and a lot of the warehouse. So maybe it's not going to be, running through, doing like running through the forest or operating in a construction environment yet, but that's a solved problem. And we're starting to get really good at deformable objects, things like cables and belts and chains. We're getting pretty good at modeling those and being able to interact with them. The hard things, which Andrew already alluded to and beat me to, is things like friction and lubrication. We're up in Toronto, Canada, and for all of you in Boston, you probably still have some ice on the ground. Ice is still a really hard problem for robots, and so is. And then the last thing that we have a hard time with is object damage. We're great until we need to rip open the box or tear the plastic wrap off the pallet. And those are things that humans do really instinctively. Like if you just want to get all of the things off of the pallet, you have to rip through the plastic, you have to, tear the tape, open the box, open the bag. Those are hard problems still. So everything's pretty good until things start getting slippery and lubricated and start breaking. In this case, literally, and in a lot of cases, intentionally.
Oh, I mean, my brain just goes crazy thinking about how much a part of, for example, a surgical environment, that is. So being able to model that for some of your end customers, as you stated, pretty important to be able to solve that. Andrew, coming back to you for a second, we recently had you on the Robot Report podcast as a guest, and it was there that we talked about the barrier control functions being provably safe compared to traditional AI. And I think it's one of the things you started with as well in your introduction. This is sort of that space that you're trying to carve out an opportunity to be a part of the entire control architecture. So can you share your thoughts about how you're implementing this concept of a theoretical aspect like control barrier function in an interaction with AI?
Yeah, sure. So control barrier functions are a relatively new nonlinear controls technique that me and my co-founders have been working on for about a decade now. And it's really picking up in academia. And the core concept behind it is that you define what safety means mathematically, so as a subset of your state space. And you essentially know that by choosing a control action within this range, which you compute at every time step of the robot, the system is going to maintain invariance of that set. So it's never going to leave that set. And so it's a very different concept from kind of a heuristic around safety, or a concept where you're just trying to kind of think out all the failure modes and what do you do with those failure modes. It's very much a constraint-based satisfaction where, let's say your system operates really well within this specific region of its state space. We can give you a formal way to know that the system is always going to stay there. And so, provably safe is a term that's used a lot in the literature when talking about barrier functions. And the terminology, what it really means is that you come up with a set of assumptions about your system. So you have a model of the system, and based off of that model, if you use this math, you know exactly how that system is going to behave. And so there's no free lunch, right? There's no way to 100% guarantee system in the real world, because you always have modeling uncertainty. You always have things that break. But it's a true formal method where if the assumptions on your system are satisfied, you know exactly what the behavior of the system is going to look like. And that pairs really well. Oh, I'm sorry.
Go ahead.
I was just going to say that pairs really well with these AI systems, right? Because AI systems are in some ways kind of the opposite, in that you can train them to work really well, but you don't have any sort of kind of certificate of how it's going to look like in certain regions. And so barrier functions can be used for a lot of really valuable things with learning-based systems. For example, they can be used to maintain the system in the region where there has been sufficient data collection to be confident about the behavior of the AI system. It can also be used as kind of a safeguard against unsafe actions that the AI system puts out. And so I think it works really well with these learning-based controllers, and it really complements their lack of determinism.
I want to ask you to give us a little more color because I know that you've had a variety of different opportunities to deploy your algorithms from the extremes of jet aircraft, right? So fly-by-wire jet aircraft being able to take an input from the pilot and determine if that's going to make the vehicle unstable, right? And controlling that, all the way to the other side of the world where we're talking about can we make humanoids inherently safe when they're dynamically stable and avoiding a trip or a fall on a humanoid. So talk a little bit about how those use cases are same, similar, different, and how your algorithmic concepts are helping to solve those different problems.
Yeah, sure. You're touching on a really critical part of control theory in general and control barrier functions, which is the fact that these are model-based control algorithms. They're not handcrafted or hand-tuned for each system, but they're a generalizable mathematical concept that you can apply to any model of any robotic system. And so we've deployed on the F-16, we've deployed on automobiles, we've deployed on mobile robots. And it's the same software that we're running on each of those systems with different configurations. And those configurations are really two parts. There's configuring, or I guess three parts, I'll say. There's the dynamics of the system, which is obviously wildly different between a jet aircraft and a humanoid. There's the perception capabilities of the system, so defining what sensors it has and where those sensors are. And then there's kind of the actual constraints that you want to enforce, which are going to actually be similar with some kind of unique additions for specific types of systems. Like you might want to enforce a stability constraint on a humanoid robot, whereas that might not be relevant for a fixed manipulator, right? And so those are kind of the three, what I'd call like user specified or engineer specified inputs that you would feed into an algorithm like this. But everything else is general in the same core backend.
And I guess important for every roboticist and motion control engineer is corner cases. So how do you handle some of the unpredictability of corner cases that traditional testing might miss?
Yeah, so corner cases and the unknown unknowns is always the hardest part of deploying the system. Robotic systems get stuck at kind of like mid scale where you've deployed hundreds of them. And they don't go into, the tens of thousands of robots, is because you haven't yet identified all of the corner cases that you're going to have to run into. And so, by shifting the methodology from kind of, testing-based safety, where you try to test every outcome of the system and verify it, to what we'd call kind of constraint-based safety, you go from, does this system work in every output, to, is this scenario allowable under the safety constraints? And are my assumptions around the system valid? So you end up having kind of this smaller space to validate, since you know how the system's going to behave, assuming your assumptions are correct. And the corner cases aren't nearly as common to come across because you actually have a control system that's keeping you inside of the set of states where you know what's going to happen to the robot system. So there's never any way to get rid of all of the corner cases, but this constraint-based methodology is one way to significantly limit the number of corner cases you see.
Yeah. So for folks listening, I haven't seen, there is an obvious thread through this conversation tying, Robert and Andrew together here, which is safety. So Robert, I want to come back to you now, give you a chance to talk about, your area of expertise. When we talk about force feedback, how does force feedback enhance robot safety? What are some of the examples there, or use cases where you're using your technology, your customers are using your technology to improve the safety of the system?
Yeah, for force sensing, you pretty much have to have it if you want to have any sort of a collaboration or assistance with people. So when we're talking about constraints-based safety, this is one of the constraints that you need to do anything from be able to hand something to a robot. It's like, here's a screwdriver, go do this job. If you want to place it in its hand and have it take it from your hand or hand something to you, everything up to having an assistive robot that's expected to actually go and to lift a person, because You want the robot to lift the person. You may not always want the robot to be lifting up people, but in this case, its job is to lift the person and to move them around for assistive robotics. So that's a constraint-based system where you want to apply enough force to lift them, but not so much force as to throw them across the room, for example. That's a big difference, and it's not something that you can do with vision or LiDAR because you actually intend to make contact with this person. So without force-based systems, you end up either running away, the robot has to run away from the person and avoid them, or they end up curling up into a safe state. So if it's a humanoid robot, just curl up into the fetal position and wait for the human to go away.
What would you say are some of the limitations then of force feedback in the actual, control loop architecture?
So the first one is inertia. So the example I give is force control is not so useful in autonomous driving. You've hit the person at this point. You can brake, but it's a little too late. So inertia is one of the big ones. The other is that you do want to, if you're just applying pure force control, so traditional cobot style, there are a lot of situations where you actually intentionally want to apply force. So a good example would be something as simple as a shovel. I actually want to break the ground. I want to apply enough force that the shovel goes into the ground. So I can't I can't make the robot weak enough that it can't do anything because I still want it to do useful work. But if I were to take that same pickaxe or shovel and apply as much force to a person as I did to the ground, that would be very, very bad. So that's one of the limitations, is you do need to give it context around what it's doing. But that's also one of the advantages if it does hit something, it can help classify it. So if it puts the shovel into the ground and it hits something metal, it can tell you that, whereas a vision-based system can't.
I think for me, a relevant example is I recently had a chance to drive a John Deere excavator. And the interesting force application there was that, you pick up a yard of dirt, and the robot, the excavator, actually tells you how much you just picked up, right? It can actually weigh the bucket and tell me exactly how much dirt so I know what I'm putting into the back of the truck. So very interesting example. Another example, you said picking a shovel, using an excavator as a big robot today.
Then I was going to just tie this back to Andrew. It's like that is one of those rules-based constraints, and one of the original ones. If you pick up a bucket and then you try and drive down a hill where you would likely roll the robot, it's not going to let you do that. It's going to either make you drop the dirt, or it's going to make you take a different route. Even though you're fine to lift that load of dirt, you're fine to go down that hill. You're just not fine to do both at the same time. So that's where that's one of the sort of original safety mechanisms.
Interesting. On the converse, then, what are some of the advantages of force feedback that you like to pitch today?
Yeah, so I think there's four big categories. The first is force control and compliance. This is the original reason we started using force torque sensors. It's for things like grinding, polishing, torquing bolts, popping parts together. What they market the original cobots, and even before that, just force torque sensors for. The next one's force limiting from a safety perspective, and this is what made cobots work. Is they weren't really collaborative robots. They were force limited robots. That was really the selling feature of them. And then the two new ones. The first is object and material identification. So you touch something, you can tell what it is. You can tell if it's hollow. You can feel the contents inside of it. You can feel around in blind areas where you can't easily get a camera into. And then the last one is world modification. It's your ability to apply force, not just to identify the world, but to, for example, rip a box open or tear through a bag. You're actually trying to apply force to break something open. or to crimp something. So actually applying force to change it once you have identified what it is. So I think those are the four big categories in sort of the order that we've been adopting them into robotics.
Yeah, I think the first one, obviously, we've talked a lot about, the Robot Report have talked a lot about the force-controlled grinding and polishing applications, and that's a big segment of the market for many, as well as assembly, pushing parts together as you assemble them as well, right? But with the emergence of cobots as a, quote, force-limited system, and I guess now the term is collaborative applications, right?
Yep.
So are force sensors necessary in the world of cobots, or if a cobot can use force torque in the robots and motors, what's the advantage or requirement for an external mechanism as well? Maybe explain that to us.
Yeah, so I guess you want to be able to measure the output. That is the actual force you're applying to the world outside. You want to be able to do that accurately. So that's the short answer. Trying to measure for motor current is very difficult, especially if you go through like strain wave gearboxes, you're going to add torque ripple on top of it. If you use traditional planetary systems, the higher the gearing you go, you're going to get more attenuation, and they're not always back drivable. So if you are moving or something pushes back on you, it can't always push that force back through the gearbox so you can actually feel it. So if you aren't actively pushing into it, it can't really read backwards. And then you do have backlash. But I think the big ones are the attenuation, the back drivability, and the mechanics going through the gearbox like torque ripple. That makes it impractical to use them as any sort of safety device, and they're usually not particularly helpful on that identification because, well, human touch is fantastically sensitive, and that is what we use to identify most of the things around us. Even if you go and go to the store, you'll still go around and you'll feel fabrics and you'll touch materials and you'll judge, even just picking up a box, shake it, what's inside it. We use that a lot. So I think the sensitivity is required beyond safety to be able to really use them as a rich input.
Yeah, interesting. So I just want to take a time out for a second and remind folks that if you have a question you want to ask our guest today, please use the Q&A widget in your console to ask a question. We are queuing those up. We've got several already, and I see them in the Q&A list here, and we'll have time here in a bit to ask those questions of our guests. All right, Andrew, I'm going to come back to you and sort of more of an open-ended, broad question. Talk to us a little bit about some of the new areas of robotics that 3Laws technology is enabling.
Yeah, sure. So robotics is in a really exciting time right now, I think. Not just because of all of the exciting, AI software stuff we're talking about, but kind of what that has enabled for form factors of robots, right? We're getting more complex geometries, more general purpose robots. And I think a lot of the kind of typical approaches to safety for, what's commonly used for fixed manipulators or mobile robots don't really scale to these highly complex platforms. And you really need to understand kind of the whole body safety problem, if you will, right? So let's say rather than for a mobile manipulator having kind of an AMR-based safety system for the base and then kind of a manipulation-based safety system for the manipulator, you want one safety layer that understands how the whole system is moving to really be able to maximize the performance of that system. And so I think that's a really unique area where 3Laws and our technology can shine, is making the safety case for complex systems with often complex constraints around safety, things like stability that are now starting to become actual safety concerns for systems.
Oh, interesting. Robert, I'll sort of another open-ended question for you as well. what innovations have come to market, with force sensing in the last decade or two? Because I remember the early days, as through hole component was and grinding were the two big applications. You mentioned a few already, but what are some of the other innovations that have come around the force sensing hardware or software?
Yeah. I think a lot of that, like similar to machine vision, it's gotten a lot easier and it's a lot more stable. So, our systems are now, they come pre-calibrated, full system accuracy rated. They operate for their entire lifetime without recalibration. They're good from, negative 40 degrees Celsius to 125. So really any environment. And they've been ruggedized significantly. The early systems were really designed to be, in an automotive like manufacturing environment where the number of disturbances they would see is, 1 in a million parts. Whereas now every task is a little different. So they've really been ruggedized to the point where, if the robot does slip, fall, has something drop on it, the sensor's fine. So I don't think of force torque sensors, with your, like they would have been 30, 40 years ago as this fragile piece of almost metrology equipment. They're now actually your more rugged sensor. If you're thinking about vision systems, if you go into, a dusty environment, a muddy environment, you're doing any sort of grinding, you're, using flood coolant, your camera's going to get dirty really quickly. Your force torque sensor is fine. So it's gone from being probably one of the more delicate systems on the robot to now one of the most robust, and it makes it a great safety system, but it also makes it great for applications where vision doesn't work well or has a hard time. So mining's another great one because there's all this humidity, and unless the robot's going to go and keep wiping its camera off all the time, force ends up being a really useful tool for those sort of dirty or less structured environments.
Yeah, thanks for that clarification, because I certainly remember the early days of force sensors. If you dropped it, you had to the recalibration was necessary because you bent something potentially.
We've had robots we've had robots with 65 kilogram payloads do a cartwheel or a handstand during some of the model training, and the sensor's just fine. So the robot isn't actually strong enough to break its force torque sensors anymore, at least not to break our systems. We typically size it, so if the robot does give a big old high five to the floor, then it's going to be just fine. The rest of the end effector is going to be pancaked, but you just unbolt it, bolt a new one on, your sensors are just fine.
The other interesting and emerging topic around this is, the relationship between force sensing and touch as well, especially in humanoids and humanoid hands, becoming such an important sensory feedback. Talk to us a little bit about how those are related.
Yeah, so we talk about them as pressure and contact mapping. So I can give you a map of where you're touching things and maybe even the texture of the thing that you're touching. SynTouch did a really good job of them. Unfortunately, I think they have shut that down. But if you remember those big green fingertips, they were wonderful at capturing texture and where things were touching, but they weren't doing force and they didn't really do shear that well. So if you wanted to tell if something was slipping out of your hand or how much force you were applying to that, you couldn't do it. The good news is there's no reason you can't stack them. Our robot fingers, they're designed so that you can just bolt them into like a robot teeth gripper, and then they have a mounting pad to put a pressure sensor on top of it. So you can get the best of both worlds. So you can, for example, if you're doing a blind bolt, you can feel around with that pressure sensor, find the hole, put the bolt in there, and then use the force to torque that bolt down, all in one motion by doing those hybrid sensing schemes.
And you talked also, surgical is one of your areas of exploration as well. How small can we make a force sensor today?
Really, we can make it incredibly small. We built them for, 5 times more sensitive than human touch. We did that for catheter robotics, so you could feel the inside of a blood vessel. We built them down to, we are going to be launching a new system. We started with doing fingers, and it's actually our current fingers are exactly the size of my finger, and we're going to be releasing fingertips now. So we've already got them out with a couple of our humanoid friends, and we're going to have those coming to the general market. So we'll have a fingertip that matches human sensitivity. So you can put that anywhere, and you can always make a bigger version of it, and then you can also have a palm as well. So we're able to get that, let's call it 16 millimeters by 20 millimeter type form factor for fingertips.
Oh, that's cool. Well, gentlemen, as we sort of try to wrap things up on our prepared interaction here, I want to ask both of you to sort of, again, zoom out a bit. And so the question to both of you, I'll ask you in sort of order here. How quickly are software controls and controls engineering evolving, and, the maturity of things like vibe coding and now AI supervised motion? Is there still an opportunity to innovate in the world of real-time controls and in control, closed loop control? Andrew, I'll ask you first.
Yeah, I think definitely. I think what, AI really needs to be successfully deployed is to have kind of lower level systems with really great response times, really robust kind of stability margins. So I think the better you can actually make these embedded control systems, the better these new technologies will be able to really leverage them to do new and exciting use cases and applications. And so I think there's always, ways to innovate and improve and further bring down response times, further increase stability. So I think there's a lot of value there still.
Rob, same question to you in terms of the innovation here.
Yeah, and I'm always adding to Andrew because we are that low-level system, and specifically for force. So there's a lot of opportunity at that edge, at that low-level system, to create context, to create intelligence. I mean, we talk a lot about AI as a very broad term. Neural nets are wonderful classifiers. They're wonderful at classifying what they're touching and how it's reacting. And then that gives you something that you can use at a higher level. I go back to the shovel example because I think all of us would prefer that the robot dig the ditch instead of, yours truly. So if it puts the shovel into the ground, it's like, this is dirt, that's a rock. Oh, that felt like plastic. Maybe there's conduit buried here, or that felt like wood. There's a tree root and I might have to go and get a maul. And all of those are things that you would never have with vision, and that could be done at a really low level. So you can say, it's like, hey, I was going through dirt. There is I've hit wood at this point in space. That's really useful contextual information. And that's something you can run with a relatively small neural net at the edge. Like, we're not talking about an NVIDIA GPU here. We're talking about maybe a little FPGA, or even just running on an embedded core. So yes, there's lots of opportunity there to give context so that those higher level, constraint-based systems have more to work with. It's, if you're digging and you hit metal or you hit conduit, stop. So recognizing what that is, just giving an example there, there's a lot that can be done.
Oh, great. That's a great illustration. So thanks again for integrating a real example into that. All right. So again, to our audience, a reminder that we've got some time left here for questions, and use the Q&A object to submit your questions. And so, gentlemen, we've got some questions lined up here. I'm going to sort of course through them in a sort of random order here. And I don't know who wants to answer this first one, but Florian asked a question, and he says, when it comes to force limits in robot hardware, how much are current system boundaries actually driven by the control strategy versus the underlying material limits of the mechanical components, such as housing, brackets, joints, and the rest? So I don't know who would like to take that one first. Robert?
I'm happy to take that one. I think it's almost entirely on the controls at this point. We can design uh, the robot so that it can't really hurt itself, so it's applying its full amount of force without damaging itself. I think that's just good humanoid design at this point. So a lot of this is coming to it is going to be on the control side of things. It's going to be contextually limited on what they're doing. If it's, helping to lift a person, or if it's grabbing something out of your hand, the robot's got more than enough force to do work, to, torque that bolt, to rip that box open, and it needs to be very ginger in those applications where it's working with people. So I think it's going to be almost entirely on the control sides of things, and those constraint-based rules, and the contextually constraint-based rules.
Andrew, do you have any color to add to that?
No, I thought that was a great answer to the question. Just kind of an
Okay.
anecdote in the aerospace realm. There's also this sense of like, when it comes to constraints, what's it really for? Is it to protect the hardware? Is it to make the human comfortable? And so, for example, there are a lot of times when we're working on the jet where we would put constraints on negative Gs, not because of structural limits of the aircraft, but because of pilot comfort, not wanting to stay at negative G too long. And so I think we are absolutely in a world where the hardware is very, very capable, and it becomes more about what's the right limits for the application.
Interesting. All right, here's the next question from Jamie. The question is, what about situations when moving outside the constrained space is the safe state to be in? Humans can assess if losing a fender or the side of the car in a crash is safer than insisting on staying on the road. Andrew, I'm going to ask you to respond to this one first.
Yeah, it's a really excellent question, because if you treat every safety constraint as equal, then you're going to arrive in situations like this, where it's like, the robot's told to, or the car in this case is told to stay on the road, but it would also have a constraint saying, don't hit this other car, right? And that's why kind of an understanding of the prioritization of constraints and encoding in that prioritization is so critical, so that you can do things like sacrifice, the loss of one constraint, like staying on the road, in order to improve the general safety. Like, safety isn't defined as stay on the road. Safety is defined as, reduce harm, minimize harm. And in that case, you should prioritize avoiding a collision over staying on the road.
Okay, good. Here's another question directed at Robert. In robotic fingers and gripping surfaces, how can sensing functionality be integrated while still maintaining a wear-resistant, durable contact surface over long-term use?
Yeah. So the good news for that is the force control, our force fingers, that's built into the bones of the robot. So you can put whatever jaws you want on that gripper. You can do soft jaws, you can do tool steel, you can do, like a Vibram rubber if you want really high grip. So you can get force control without sacrificing the existing surfaces that you already use. So there's really no change there. Pressure mapping will change that, but for a lot of applications, you can get away with force. And the way that I explain that to people is most tasks in industry are achieved while wearing work gloves. So you still have force control, you still have your wrists, you still feel a lot of things, but your pressure mapping is impaired by those, leather work gloves. So if a human can accomplish the task while wearing work gloves, then you can do this likely without pressure mapping, but you'll still likely need force control. So there's really no trade-off if you can get away with just force control, and you can tell if you can get away with force control usually if a human can do it wearing work gloves already.
Interesting way to describe it. Thanks for that. Andrew, another question. This comes from Callum. Would the 3 laws layer sit above the traditional control loop layer, and would it generate reference values for the lower level control loop that fit the constraints based on the context of the situation?
Yeah, it's a really good question, because it depends. It depends highly on the application, and it depends on what exists in order to be used. So, example, if you're flying a jet, those aircraft have incredibly good surface controllers with hundreds of pages of stability analysis on those controllers. And so we would absolutely want to leverage that. And we would want to operate at a level higher than that. For example, we're controlling the pilot station G-forces, the roll rate of the aircraft, and not the actual surface deflections, because there exists a certified controller there already. I think in the case where you want to do a whole body learned controller, and you have this kind of non-deterministic, unable to be certified control layer, we would want to actually be past that. We would want to be at the torque component, so that we can actually do the safety constraints on the output of the non-deterministic layers.
Interesting. Yeah, good. Thanks for that response. The next question I'll direct at Robert. This comes from Ahad. The question is, when building force sensors for surgical applications, what design considerations go into choosing the right technology or form factor?
Yeah, well, I think the first one is what level of sensitivity do you need? Because remember that a surgical robot is often already amplifying human motion. With most surgical robots, you're operating at 2 to 5 times magnification already. You're already magnifying your motion. You're already magnifying your vision. So you probably want to match the amplification of human touch to match that. So you're trying to recreate what the surgeon had before. And in some instances, it actually is, it's clinically useful to have superhuman touch. So a good example I give is for catheter robotics. Being able to feel the catheters, especially the guide wires, going through the blood vessel is right at the edge of human perception. So being able to have 5 to 10 times amplification is actually really clinically useful. So the first one is, what's the resolution that you need to be able to do this work? And then in terms of the form factor, surgical robots are incredibly space constrained. So it's trying to figure out where you can get it, especially into the end effector, so that you can measure the forces at the business end of the surgical instrument, at the distal tip. So those are the two biggest ones. And then the last one that people typically don't think about is the sensor needs to be stable over the entire surgical procedure, and typically up to 75 degrees Celsius, because that surgical robot has nowhere to exhaust heat. So imagine you took a humanoid robot and you put it in a plastic bag and it didn't have the ability to exhaust, use convective cooling. Surgical robots are typically operating at 75 degrees internal temperature. So it has to be a really stable temp sensor, both over time and over temperature. And that's something that humanoid robots is going to need some amount of as well. So there's a lot of great technology from the surgical robotics market that you're going to see spill over and get cost optimized for the humanoid and for the physical AI space.
Robert, thank you. Yeah, that's a great answer. And I don't often think about the heat involved there, but it's certainly important for sensor design and sensor performance. So another important consideration. All right, so I think we have time for one more question. This one's going to go to Andrew, and it comes from Mata. The question is, do you have any recommendations about the available open source foundation models as the starting point for fine-tuning motion control of mobile robots, maybe and adapted to ensure safety requirements? So yeah, lots of evolution these days about this concept of a foundation model.
Yeah, and I think we're in the really early days, especially when it comes to the open source models that are available. I think most of the high performance things we've seen are out of closed source models from companies like DeepMind. But there are some kind of flagship open source VLAs. So a VLA is a vision language action model, which is kind of a subset of foundational models that you can use and run, like OpenVLA from Stanford, I think is probably the best flagship example of an open source foundational model. But we're still in the really early days, so I wouldn't expect people to be able to, download and fine tune these and get better results than they would out of a more traditional control method.
All right. Well, gentlemen, it's been an amazing conversation. I want to thank you for your time. I hope I did a good job here of sort of stitching together a conversation thread between your two technologies, but it's always interesting to learn about the innovation that is happening, around the most basic elements of a robot, which is its motion control system. And the conversation today has been very enlightening. So I want to thank you for that. And I want to thank everybody for attending today. That's all we have time for. And I want to thank all of our sponsors as well who made this possible. So thanks to Navanta, Bokers, Meanwell, Electrocraft for sponsoring the event today. Our next webinar will be on April 15th on the topic of best practices for robot design. You can sign up for that at the Robot Report website. I hope you'll join us. So once again, thanks to Andrew Singletary, 3Laws Robotics, and Robert Brooks from Force N for sharing their knowledge with us today. I hope you'll take a moment to fill out the survey at the end after the webinar ends to give us feedback about what you enjoyed or didn't about this session today. I also want to thank our producer, Lindsay Harvey, and the rest of the WTWH webinar team for their hard work on this series. I hope your 2026 is off to a great start. My name is Mike Oitzman. Thanks again, everyone, for attending.